In section 3.4, we will be discussing ionic nomenclature. So, first of all, we should clear up what we mean by nomenclature. Nomenclature is just simply a naming scheme. So in this case, we're talking about the naming scheme of ions and ionic compounds. So chemical nomenclature is the system used to distinguish compounds from each other and the rules used to devise their names. The rules that we're going to be using are those devised and developed by the International Union of Pure and Applied Chemists. Now, it is important to recognize that there are many common names that people frequently use, especially in the health sciences. And a good example of this is the term water. These are not part of the IUPAC system, and you'll just kind of have to get used to using those. But what's important for us is when you're asked to name a compound, that you use the IUPAC rules and not the common names. So the first thing that we need to recognize is that ionic compounds are named according to different rules than molecular compounds. Typically, an ionic compound will result from the formation of a metal with one or more nonmetals, whereas covalent or molecular compounds result from the combination of multiple nonmetals. So before we can decide how we need to name a compound, the first thing we have to decide is it ionic or is it molecular? And the easiest way to do that is look for the metal. So sodium chloride here begins with Na, the symbol for a metal, so therefore it's ionic. Barium chloride here begins with Ba, the symbol for the metal barium, so therefore it is ionic. Magnesium oxide begins with the symbol Mg for magnesium, a metal, therefore it's ionic. Whereas NO2 begins with the symbol N, which is for the nonmetal nitrogen, so therefore is molecular. Carbon dioxide begins with the symbol C for carbon, which is a nonmetal, therefore CO2 is a molecular compound. And then CH4, also known as methane, begins with the symbol for carbon as well, and carbon is a nonmetal, so that's a molecular compound. So once you've determined that your compound is ionic, you can name it according to the rules that we're going to be developing in this section. It's important to recognize that we use different rules for molecular compounds, and we're going to learn about those a little later. The types of compounds that we're going to be learning how to name are what are referred to as binary compounds. A binary compound is one in which there are only two types of atoms present. Specifically in this section, we're going to learn how to name binary ionic compounds. And a binary ionic compound is one in which we have one element that's a metal and one that's a non-metal. So that doesn't just mean that there's one atom of non-metal and one atom of non-metal. You can see here, this compound Na2O, there are two sodium atoms and one oxygen atoms. It's all about the types of atoms. There's only one type of metal, which is the sodium, and one type of non-metal, which is the oxygen. Here we see the opposite scenario, where we have a compound where there's one copper ion and two chlorine ions. So again, even though there's more than one chlorine, there's only one non-metal and one metal present, so we classify this as a binary ionic compound. Now, in order to begin creating the names for ionic compounds, we first have to learn how to name what are referred to as monoatomic cations. And monatomic cations are formed when metals lose electrons. They can be grouped into two types. There are those what we call fixed charged cations, and they contain a metal that consistently forms an ion of a particular charge. And these are metals from group 1A, group 2A, aluminum, gallium, silver, zinc, and cadmium. The other kind of monatomic cation are what we call variable charge cations, and they contain a metal that can form more than one type of positive ion. And basically they're anything that's not in the list above, and most of these guys are found in the B groups of the periodic table. So just recapping, silver, aluminum, gallium, zinc and cadmium form only one ion along with the metals from groups 1A and 2A. In particular, silver always forms a +1 cation, aluminum always forms a +3 cation, gallium always forms a +3 cation, cadmium always forms a 2+ ion, and zinc always forms a 2+ ion. How we name these ions is by giving the name of the metal, completely unordered, followed by the word ion. So for example, if I wanted to name this cation, I would realize that sodium is in group 1A, so always forms a +1 cation. It is a fixed charged cation, so we just name this as sodium ion. Aluminum, as we pointed out previously, always forms a 3+ ion, so again we just take the word aluminum and add the word ion to the end. So that's pretty easy. But what about those variable charged ions? So some metals, mostly from the transition metals and a few from group 4A through 5A, can form more than one cation. So famously, iron forms an Fe2+ and an Fe3+ ion commonly. Chromium commonly forms a Cr2+, Cr3+, and Cr6+ ion. Cobalt forms cobalt 2+ and cobalt 3+ commonly, and copper commonly forms copper 1+ and copper 2+. So in these cases, we're going to have to make it clear what the charge on the cation is when we name it. And we have a pretty simple system for doing that. It's often referred to as the stock system. So when we write the names of variable charge metal ions, we need to specify the charge by putting it in Roman numerals after the element name. And we also put that inside parentheses. And you might see this referred to, as I mentioned before, as being the stock system of naming. So Cr2+, we know that Cr is not silver, it's not cadmium, it's not zinc, it's not aluminum, it's not gallium, it's not in group 1A, it's not in group 2A, so we need to specify the charge. And it's pretty simple. You give the name of the metal, followed by the charge in Roman numerals, and then you just add the word ion to the end. Let's look at this guy. If we want to name this one, we go through the same process. It's not silver, it's not cadmium, it's not zinc, it's not aluminum, it's not gallium, it's not in group 1A, and it's not in group 2A, so we're going to need to specify the charge. So we're going to write the name of the metal unaltered, and then we put the charge in parentheses using Roman numerals, it's 3 this time, and then finish it off with the word ion. And that's it. And so now it's very clear whether we're talking about cobalt 3+ or cobalt 2+, chromium 2+, or chromium 6+. There's no ambiguity. Now, there is a older, sort of slightly old-fashioned way of naming these variable charged cations, and it's a little bit complicated. What we do is we take the root name of our metal ion, so the first syllable of the metal's name, and then we add the ending us to the ion with the lower charge, and the ending ik to the ion with the higher charge. So we get pairs like chromus, chromic. For chromium 2+ and chromium 3+ respectively, we get cuprous and cupric. For copper 1+ and copper 2+. And we get ferrous and ferric for iron 2+ and iron 3+. Now you can kind of see an issue here because, you know, sometimes the OUS is 2 and sometimes the OUS is 1, sometimes the IC is 3, sometimes the IC is 2, so it's kind of like a little bit all over the place. I tend not to use this system because it requires you to know that there is a higher charged cation and a lower charged cation, but you will see this in the medical field. Here's a table that illustrates a few more examples. It should be noted that the stem name for these elements is the Latin stem, so that adds another complication sometimes for some of these elements. So they're not just giving the first syllable of the element's name, they're giving the Latin stem, so you need to know that. And so that's why I don't really like this system, but we end up with things like ferrous, ferric, cuprous, cupric, stannous, stannic, plumbous, plumbic, etc., etc. I'm not going to hammer you on this, but it is worth knowing, and you should be prepared to look this up if you see it written somewhere. So we know how to name cations now, but how about naming monatomic anions? And this is a pretty easy process. We take the first syllable of the element's name that's forming the anion, and then we just add the letters IDE to the end, followed by the word ion. So we're going to end up with things like bromide ion, chloride ion, oxide ion, sulfide ion, phosphide ion, etc. And note, we never need to specify the charge, because for the nonmetals that form monatomic anions, we can always deduce the charge from the position in the periodic table. Those elements that are in group 7A form -1 ions, those in group 6A form -2 ions, and those in group 5A form -3 ions. So no need to specify the charge, we just have to look at the periodic table and figure out what it is. So here are some examples. These first three are what we call halide ions because they are formed by the halogens: fluoride, chloride, bromide. So these first four are halides. Then we have some ions formed by group 6A elements. So we have oxide ion and sulfide ion. And then finally we got some elements formed by group 5A elements, phosphide ion and nitride ion. So you can see, take the first syllable of the element's name and add the letters IDE followed by the word ion when we're naming an anion. So how do you name the whole compound? It's pretty easy. You give the name of the cation and then you follow that up with the name of the anion and you eliminate any occurrence of the word ion. So I would name this guy as iron 2 oxide. I have to specify the charge on the iron because it is not a fixed charged monatomic cation. Sometimes iron forms Fe3+. Sodium is in 1A, so that means that it is a fixed charged cation. So I can just go ahead and name this guy as sodium chloride. So here's a little flowchart helping you name ionic compounds. First thing we're going to do is identify the cation name and the anion name. So the first question we want to ask ourselves is, can the cation have more than one possible charge? And if the answer is yes, we're going to have to use the stock system to name the cation, which means we need to determine its charge and then give the metal that is forming the cation its name, followed by the charge in parentheses. Once we've done that, we can then add on the name of the anion, and that's pretty easy. We give the stem of the cation name, just the English stem, and then we add the ending to it, IDE. So we're looking at things like iron 2 chloride, chromium 3 oxide, etc., etc. Now, if we decide that our cation cannot have more than one charge, then it gets a little easier. We give the name of the cation, we don't need to specify the charge with Roman numerals, followed by the name of the anion. So we have potassium bromide, sodium nitrate, ammonium sulfide. Okay, so this is an exercise from the book. It says write the formula for each ion. So the first thing I'm going to do is decorate my periodic table with the charges that I know are formed by different elements. So everything in group 1A forms a +1, everything in group 2A forms a +3, aluminum and gallium in group 3A form a +3, silver forms a +1, cadmium a +2, and zinc a +2. So in A, fluoride over there, it's going to be F single minus. Now, if an ion's name ends in ate or ite, that means that it is a polyatomic ion. So under those circumstances, what I'm going to have to do is I can't use the IUPAC rules to figure out the name of the ion. I have to go to the table that you were asked to memorize earlier that had those 10 polyatomic ions in it and find the formula that corresponds to carbonate. So there's really nothing for it. You just have to kind of recall that from memory or look it up in the table. This one's going to be a little bit weird. Ferrous. So I got to remember that ferric and ferrous, that this is the lower, this is the higher. So this is Fe2+, and this is Fe3+. So ferrous is Fe2+. Okay, now potassium ion, find potassium in the periodic table, and we see that it's in the +1 column, so we can just go ahead and write that in as +1. When it comes time to name ionic compounds, we want to be mindful of if we have the presence of a polyatomic ion. And there are 3 cases where we've got polyatomic ions here. And when we have a polyatomic ion, we have to just look the names of those ions up in the table. So the cation in our first compound is calcium ion. And we can see that calcium is in group 2A, so it's 2+, and because it's a fixed charged cation, we don't have to specify the charge. So this guy's called calcium. Now, PO4, and the charge on this one's going to be 3-. Sort of figured that out because if I needed 2 calciums, that would give me a total charge of 6+. So I must have made a total negative charge of 6- to cancel that out. Alright, so I have to go find the name of that guy, and when I do look it up in the polyatomic ions table, it is phosphate. So this compound in A is going to be calcium phosphate. You just squash the name of the cation and anion together. The next one is somewhat similar. We can see that we have 2 polyatomic ions here. We have the one NH4, and then we have Cr2O7. So with the polyatomic ions, really to begin with, you kind of have no choice but to just look them up in the table. So NH4+, and we have 2 of those, giving a total of 2+ charge. That's the ammonium ion. and again I look it up in the table. It's one of the rare examples of a polyatomic cation. And then Cr2O7, it must be 2 minus because we need a total of 2 minus charge. When I look that up in the table, I see that that is called dichromate. So putting those two together, we would call this compound ammonium dichromate. And note we always put just the cation name followed by the anion name. Alright, the rest are a little easier because we don't have any polyatomic ions present. Whenever we see more than one non-metal, more than one type of non-metal, we always know that we've got a polyatomic ion that we're going to be dealing with, and it kind of makes you take pause and grab your table of polyatomic ions because you know you're going to have to look up the name and the formula. Alright, so potassium is in the group 1 column. We only got one of these guys. And then chlorine is in the -1 column, group 7A. And we got one of those. So our cation here is not a variable charge, it's a fixed charge, so we just write its name. And then we're going to follow that up with the name of the anion, which is pretty easy. We just take the stem name of our nonmetal and add the letters IDE to the end. So that's going to be potassium chloride. Now, the next one is a little bit more mysterious. Copper's in a B group there. It's not a fixed charged cation. Chlorine is still in 7A, so it's going to be -1. So that must mean that the copper has to be +1. So we're going to write this as copper, and because it's not fixed charge, we have to specify the charge copper 1 chloride. So not too bad, chloride, because to name the monatomic anion, we take the stem name of the nonmetal, and then we just add the letters IDE to the end. So Cl- is chloride. Now we're kind of getting in a groove now. Our next one is involving tin, and tin is not one of our fixed charge cations, so we're going to have to figure out his charge. Now we have two fluorines, and they're both in the -1 column, so it gives a total charge of -2, and that must mean that the tin is +2. So this is going to be tin. We have to specify the charge 2 fluoride. And again, the fluoride, because the nonmetal, the anion is named by taking the stem name of the nonmetal and adding the letters IDE to the end. This is going to take a little practice. We'll do plenty of these in class. Okay, so that concludes the section on ionic nomenclature, and I hope you enjoyed the video.